Let me first explain what I mean the artificial ISI. Artificial Irreversible Interference ISI refers to the deliberate introduction of distortion in a communication signal to achieve a specific purpose, especially in the SerDes design. I will describe why we need the artificial ISI for DFE design and verification. If you review the decision feedback equalizer DFE, you will appreciate the DFE not only cancels the reflection from discontinuities, but is also away from the noise or crosstalk amplification. However, you are aware that the biggest challenge is to cross the first step timing. So, you must spend most of your time designing or optimizing the first step timing over different input swings and different channel routes. Unfortunately, you cannot tell if the issue came from the first step feedback timing or the second or the following steps timing issues. Could you tell me why? Think about the input sensitivity for 5 seconds. Bingo! The input swing over I high will determine the clock to Q delay of the sample, which dominates the feedback loop timing. Again, the whole loop delay, including the sample's clock to Q delay, feedback path delay, summing nodes sampling time, and sample's setup time, must be within 1 UI. Take the 2-tap DFE as an example and assume the channel may only have 2 post cursors. To get rid of the 2 post cursors, both taps must meet the timing. As you can see, the input analog signal could be only 50 to 200 mV peak-to-peak differential, and the sample's output would be in full swing, which is also the input of the next tap. If we look at the difference between the first and second tap closely, we notice the difference is their sample's clock to Q delay and their input swing. Please be advised that the sample's clock to Q delay will decrease if the input swing is increased and vice versa. So, the second tap delay will be only 20 picoseconds. Since the second sample's input swing is at 1 volt digital level, so the critical timing is at the first tap. Another image for you is that the first sampler needs to take the tiny input swing to convert or regenerate the full swing by the positive feedback. Therefore, a simple delay image might tell you that the bigger input swing may take a shorter time to reach the full swing at the output. Is my statement here really true? In other words, is the first tap always having a longer delay time than the second tap? Yes or no? If we are only looking at the first sampler and the second flip-flop's input sensitivity, which is the clock to Q delay versus the input swing, the answer is yes. Therefore, we like to increase the input swing of the samplers to decrease the clock to Q delay and increase the first tap's timing margin. But if you are looking for more factors that could impact the input swing of the first tap sampler, you will make more reasonable assessments for the input swing after the summing amplifier or summer output. For example, if you had a poor preceding CTLE before the summer, the first step would not have enough swing to meet the timing. Therefore, if you run a 30 dB channel loss along with a good CTLE compared to a 20 dB channel loss along with a bad CTLE, then the DFE's first step may meet the timing at the 30 dB loss compared to the 20 dB loss, which might not make sense, but it did confuse you. What's the next confusing factor you might face? Think about the other DFE tabs other than first tab for 5 seconds. Great. It's not necessary that the first tab has the maximum feedback timing than other tabs. Instead, I've seen people make the second or other tab's feedback timing greater than the first tab accidentally. How could that be? Yes, the flip-flop could be transmission gate type flop and has a longer clock-to-cue delay than the sampler under a big enough swing. Also, the flops may require a longer setup time than the strong arm latch. Furthermore, the signal routing over feedback buffer design might not be optimized well enough. And then, indeed, the first tab's feedback timing is really shorter than other tabs. Then, the total loop delay at other tabs, second, third, nth tab could be longer, and then degrade the I high at the first tab sampler's input. Then, you saw the first tab cannot meet the timing and was blamed for its poor sensitivity, which is not true. In order to avoid those confusion factors in the DFE timing design phase, what should you do? Think about the reduction image for 5 seconds. Bingo! If the CTLE or other tabs could confuse the result, then why not only look at the tab you like to see? Unfortunately, from the single shot response after 30 dB loss with a single tap DFE, then not only the big precursor or other long tail post cursor still exists, then you will see the eye is still closed and you cannot really see the first tap's sensitivity, not to mention its timing information. So you probably know the issue from the single shot response that we need to have only ISI at the first post cursor, not other post cursor or even the precursors to verify the first tap properly. Think about your artificial ISI image for 5 seconds. Correct. We can make the artificial ISI starting from the single shot again. To capture how that works, let's review with a few single shot images quickly. If the single shot is feeding through a lossless channel and sampled at TS for multiple shots 1101 bit stream, there's 0 ISI at the data samples, which assumes the sampling point at the middle of the single bit or I to get the best timing margin for the data. On the other hand, if the single pass is feeding through a lossless channel, but adding the first post cursor to mimic an artificial ISI 1 plus 0.5 Z of minus 1, the current bit may create a non-zero value at the next bit sample point TS1, and that would be the simplest ISI for our case study image. For example, with a multiple plus 1010 or 1101 pattern, the data sample will be plus minus 0.5 or plus minus 1.5. So this would reduce the signal's sample swing or voltage margin, and then the sampler has a higher probability of making the wrong decision under the random noise. Please advise that even one post-cursor artificial ISI will limit the sampler's sensitivity over timing if the sample input swing is reduced because of the first tap ISI. What can we do? Correct. Remove the problematic first post-cursor completely by zero forcing, presumably in the single shot example. Once this was done, the multiple shots bit stream may get ISI free completely at the data sample again with a 2x sample input swing, which would improve the sampler's timing a lot. Of course, the first post-cursor was assumed that the DFE would meet the 1 UI timing at these artificial ISI-free conditions and the corresponding input swing. So, what's the maximum cross timing delay we can tolerate? Think about your timing issue for 5 seconds. Bingo! The allowed maximum delay is 1 UI. Everyone has a very good cross-loop delay image now. If the delay is past within the 1 UI, the next data sample will not sample the residual ISI 0.5. Again, a lot of experienced engineers don't understand the 1 UI criterion well, so this delay image should be very important for your DFE understanding. Then, the idea of the first tap DFE spice estimation or verification in the design was to check the closed loop delay within the 1 UI and see how much margin you will have over the PVT conditions. Okay, after understanding the single shot and multiple shots concepts, how do we implement the artificial ISI? Think about the super precision image for 5 seconds. Correct. The super precision implies the FIR implementation you already know. Then, for the C1 equals 0.5 of the first post-cursor coefficients, applying the input swing plus minus 40 mV, and you will get the long run swing plus minus 60 mV, but the 1010 clock pattern swing to be only plus minus 20 mV. This simulation shows exactly the multiple shots artificial ISI was discussed. Then, what's the artificial I and equalized I look like? Think about the multi-level and 2 levels for 5 seconds. Yes, as you can see, the main cursor has 2 levels. Adds the first cursor another 2 levels in combination, and there are 4 levels shown here. The minimal inner eye height is 40 mV peak-to-peak differential, which shows that the artificial ISI has a 6 dB swing reduction from an ISI freeze 80 mV peak-to-peak differential. Then, the equalized I by the DFE may get the minimal inner eye height back to 80 mV peak-to-peak differential. Those results are expected from your mental model. But what do you need by using the artificial ISI? Sure, timing check. So, you need to check the timing of 1 by 1 stage or nodes. For example, the clock's rising edge triggers the sampler to make the output toggle from the sampler's output to buffer output. The total delay was 40 picoseconds. Then, the buffer drives Summers differential pair and with another 30 picoseconds for the current switching, completing around 90% of the full current steering. The simplest setup time was 5 picoseconds in the design. Therefore, the total closed-loop feedback timing is 75 picoseconds, which has another 25 picosecond margin for 10 gigabit per second operation in the first tab DFE, not other tabs. But you can apply the similar verification approach to verify your other tabs timing individually and optimize each tab one at a time if needed by using the artificial ISI in FIR. Here are a summarized image of why you may need the artificial ISI for DFE design and verification. If you know the decision feedback equalizer DFE, you should know that DFE should make the right and fast decision to cancel the unwanted ISI or interference. Therefore, the feedback timing is very critical. Otherwise, it could be too slow to cancel the ISI. If you are a DFE designer or project lead, the DFE feedback timing should be in your simulation checklist. Unfortunately, you might check it with any channel model, either in a 20 dB or 30 dB loss. Then the first tab DFE would be highly tied to the CTLE performance. Oftentimes, the first tab DFE's input sensitivity may be good enough, but the poor CTLE sensitivity may degrade the DFE timing, and you could blend the wrong blocks. Similarly, the DFE designer could pay too much attention at the first tab, which is usually the most challenging one, but overlook other tabs, which might have a greater feedback delay and degrade input I and desensitize the first tab input swing over output timing. So, we must verify each tab one at a time, respectively, without the CTLE. Unfortunately, the individual timing check of each tab was impossible with the real channel loss in 20 dB or 30 dB. Instead, we must apply an artificial ISI in the FIR so that you could verify the timing from each stage or no. Then, either sign off your design before the tab out or re-optimize each tab one at a time during the design phase. I hope these simple design tricks in the DFE will help you. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.